You tap your phone screen, and a video plays in seconds. You probably take it for granted. Wrong. Behind that tap is a massive invisible logistics empire running at full speed. Today, I'm not going to drown you in low-level code. I'll use down-to-earth analogies to walk you through how the internet actually works. Here's the headline. Every time you tap, tens of thousands of data packets run a wild obstacle course. Let's break down the hardware of this empire. There are really only three pieces. Piece 1. The edge. Think of it as the buyers and sellers of the internet. Your phone and laptop are the buyers. In tech speak, we call them clients. Those high-powered machines tucked inside data centers the size of warehouses are the sellers. We call those servers. Every time you stream Netflix or scroll a page, the client is basically placing an order with a server. Like every play, every like, every refresh is a tiny order going out. But here's the thing, you can't just walk into the data center and plug your phone in. The network is what connects buyers to sellers, the invisible pipes that carry every order across the internet. The access network is like the side road that runs from your front door to the main highway. At home, optical fiber is your private driveway, fast and dedicated. When you step outside, your phone connects through cellular towers. That's your wireless highway. Same internet, two different access roads, but both dead end at the same on-ramp. That on-ramp is the router. It's the traffic cop that decides which data goes where. Every device in your house gets a private address from the router. Picture it as a giant interchange made of overpasses and intersections. In that interchange, there's one key piece of hardware called a router. Think of the router as the hardest core traffic cop at every intersection. Its entire job is to glance at a packet's destination and shove it toward the right next intersection, so nothing gets lost. Here's the question. The packages we order, all those video and text files, how exactly do they travel down the road? So tens of thousands of packets never get lost. In fact, network engineers came up with a super clever technique called packet switching. Imagine you bought a giant Lego set with 10,000 pieces. The seller would never pack it into one colossal box and ship it. They'd break it apart in the back and ship 10,000 separate small boxes. Each small box holds only a few pieces. In tech speak, those are data packets. What is even crazier? Every single box gets an origin and destination address stamped on it, right on the outside. It even gets special markings using specific network rules. Then those 10,000 boxes each head out like Uber riders. Under the dynamic control of this big shot protocol, they each pick totally different routes. Some take the elevated highway, some cut through side streets. They land at your doorstep at different times, in scrambled order. But don't worry. Once every box is here, your phone reassembles them, piece by piece, back into the original shape in an instant. So that's packet switching. Break it down, address every piece, route dynamically, and reassemble at the destination billions of times a day. They arrive at your door at different times, in scrambled order. Packet switching has two hardcore advantages that nothing else can match. First, it lets tons of devices share the same road simultaneously, squeezing every last drop out of idle bandwidth. Second, it is terrifyingly resilient. If one main highway suddenly jams or goes down, the other packets immediately get the memo and auto-reroute through other clear side roads. No central dispatcher, no single point of failure. The network heals itself in real time. Your video never stutters. First, it lets tons of devices share the same road simultaneously, squeezing every last drop out of idle bandwidth. Second, it is terrifyingly resilient. If one main highway suddenly jams or goes down, the other packets immediately get the memo and auto-reroute through other clear side roads. Your video never stutters. That's because every packet follows a set of traffic laws called network protocols. They are the traffic code of the digital world. Think of TCP as an obsessively strict butler who guards delivery quality. It makes absolutely sure nothing gets lost between you and the other side. It stares at the sequence numbers and checks, did any box go missing on the road? The moment it notices a box has timed out, it instantly triggers a retransmission. It tells the seller, send it again. until every last one is accounted for. IP, Internet Protocol, the address system of the Internet. The second must-have rule is IP, Internet Protocol. It does one thing and one thing only, handing out addresses. The moment your device connects to the network, it assigns you a unique digital house number. Whether the older V4 format or the current V6, the goal is the same, making sure every single data packet can land precisely on your front door. From any address to any front door. IP, precise delivery, every packet, every time. On top of TCP and IP, engineers built different communication modes for different jobs. The first one is what you see every day in your browser. HTTP, the web's rulebook. HTTP uses a classic request-response pattern. It's the traditional buy and sell model. You say, "Give me this." The server says, "Here you go." One question, one answer. But if your app needs real-time updates, like watching a stock ticker or gaming online with friends on Discord, you need a fancier protocol. It sets up a persistent two-way channel, like a phone call, streaming data with near zero delay. The Internet isn't one big magic trick. It's built on a stack of 4 layers, each with a specific job. Application, transport, Internet, link. 4 layers, 1 pyramid. This is the TCP/IP stack. From the apps you tap to the cables under the ocean, each layer talks only to its neighbor. That's the genius of it. At the very top sits the application layer. This is where your browser, your email, your apps live. HTTP, SMTP, DNS, these are the languages apps speak. When you type a URL, your browser crafts an HTTP request. The server answers with an HTTP response. Application layer, doing its job. SMTP delivers your email. DNS turns names into numbers. FTP moves files. All of them live here, in the application layer. The application layer is where humans meet the machine. It's the only layer most people ever see. One floor down, the transport layer. Think of TCP as an obsessively strict butler who guards delivery quality. TCP chops your data into numbered boxes, checks every sequence number, and screams retransmit the moment one goes missing. And then there's UDP, TCP's fast, reckless cousin. No sequence numbers, no retransmission, no guarantees, just pure speed. Perfect for live video and gaming. Transport layer, TCP for reliability, UDP for speed. 2 tools, 2 different jobs. Going deeper, the Internet layer. This is IP's domain, the global addressing system of the Internet. Every device gets a unique IP address. IPv4 gave us 4.3 billion addresses. IPv6 gives us 340 undecillion. We won't run out. Routers read the IP address on every packet and decide which way next. Hop by hop, across the planet, your data finds its path. IP wraps your data in an envelope stamped with FROM and TO addresses. That envelope is what routers read. The content inside? None of their business. The Internet layer is the postal service of the digital world. Every packet, stamped, routed, delivered. Finally, the bottom, the link layer. This is the physical world cables, fiber optics, radio waves, network cards. Ethernet cables carry signals as electrical pulses. Fiber optics use light. Both do the same thing, move bits from one network card to the next. Wi-Fi replaces the cable with radio waves. Same link layer job, getting bits from device to router just without the wire. The link layer handles the physics. Ones and zeros, turned into signals, shot through copper, glass, or air. 4 layers, application, transport, Internet, link. Each does its job. Each trusts the layer below. That's the TCP/IP pyramid. That's how the Internet actually works. Encapsulation, the Russian doll journey of every data packet. It starts at the application layer. Raw data is born here, a video frame, a chat message, a web request. The data falls to the transport layer. TCP wraps it with a header, sequence numbers, port numbers, reliability checks. Down to the Internet layer. IP wraps another header, source address, destination address, the digital postmark. Finally, the link layer. A frame header and trailer wrap the entire bundle for physical transmission. What you get is a thick nested bundle. Data inside, TCP inside, IP inside, a link frame, a digital Matryoshka doll. The bundle shoots through fiber, copper, or radio waves, traversing routers and switches across the planet. At the destination, the unwrapping begins. Link layer peels off first, then IP, then TCP reverse order, bottom to top. At the very top, the original data emerges. Exactly as it was sent, no damage, no interference. Every layer does its job, none interfere. Encapsulation, the internet's most elegant design pattern. The obstacle course behind every tap. Let's recap what we've learned across these 15 chapters. Hardware, 3 pieces: edge devices, access networks, and the network core, the physical foundation of the internet. Packet switching, breaking data into numbered boxes, the Lego strategy that made the internet fast, fair, and robust. TCP and IP, the strict butler and the postal service. Together they guarantee every packet reaches the right door. The TCP, IP 4-layer pyramid, application, transport, internet, and link. A stack of specialized workers, each with one job. Encapsulation, the Russian doll journey. Data wrapped in TCP, wrapped in IP, wrapped in a link frame, then unwrapped in reverse. Next time you tap your phone screen, remember the logistics empire running at full speed behind it. Subscribe for more deep dives.